everybody, welcome to week 14. We're going to have our last week of the semester before our exam. We have one more theorem to cover, so let's get started. Okay, so today we're going to look at Stokes' theorem. This is an extension of Green's theorem into three variables. So remember, for Green's theorem, what we're looking for is a line integral. My f dotted with dr tells me I have a line integral, and c is the path that the line integral follows. And we're going to define what's called the circulation density at the point. So what we do is, if we take a point in the vector field, we look at a small circle around there, and we look at the line value of the line integral divided by the area of the shape. So that's like an average circulation, or average amount of work done on the path. Okay, then we take the limit as the area of that circle goes to 0, so this gets smaller and smaller and smaller. All right, so that's the idea, to find the circulation density at a point. Yeah. So, but let's come back and look at a little bit of intuition. Okay, so remember what we're looking for curl. If we have something that looks like it actually curls around a point, then we're going to say it's got a curl. And now we're going to start to follow the right-hand rule. All right, so when I look at this function, and come back to the origin, I've got the same amount of stuff going out of that point everywhere that I've got, right? There's no curl. Everything seems to be perpendicular to this. So the curl at the origin here is going to be 0. Okay. Now, when I look at this one, okay, everything is going counterclockwise. All right, if I think about the right-hand rule following those vectors around, my thumb would be pointing in the negative z direction. If that's hard to see, we can talk about it in class on Tuesday and Thursday so that you can actually see it happen. Okay, but since I've got the x and the y here, the z-axis is coming towards us, which means the negative z-axis is going in the opposite direction. So this has definitely got some curl around the origin, and that curl is going to be a negative curl. All right. And this third one, if you can see, all of these vectors are pointing to the right, but you can see that they're much bigger above the x-axis. So if I have a point in the origin, things are going to push hard this direction, and they're going to push but not very hard below the x-axis. So this thing is going to end up spinning clockwise. Okay, and since that spins clockwise, if I follow the right-hand rule, now my thumb is pointing up toward me, so my thumb will be in the positive z direction. So this has positive curl. Curl's not so easy to see, though. I mean, this works pretty much, but there are times where it doesn't work very well. And let's look at this example. If you think about having a little twig, if these were water currents, if you have a twig in the x direction for this vector field, along here, that part of the twig is going to be pushed up, and over here, this part of the twig is going to be pushed down. So this twig would go in a counterclockwise direction. Which means that it should have positive curl. But now let's think about a twig that's sitting on the y-axis. Now this side of the twig goes to the right, and down at the bottom of the twig it goes to the left, which means it would go in a clockwise direction. Which means it should have negative curl. So it's not always easy to see. It's not always easy to when we're looking at a vector field. But we'll leave it there. because we're going to get into some more theory that talks about how to actually calculate curl. Now, in two variables, this was our definition of curl. If we had a vector function that was f1 times I plus f2 times j, we use that function to define curl. In three variables, we can't use that because what happens to the f3? So this is how we calculate the curl. Okay, it's that del that we talked about before, but now we're going to take the cross product with f. And our n, which will be our perpendicular vector, will follow the right-hand rule. Now, it seems kind of strange to have two definitions for this, but let's think about what's going on in two variables. If I take my function f and I add a 0 times j, now I still have a two-variable function, right? It doesn't have a third coordinate. That third coordinate's always 0. Let's look at what happens if I take del crossed with that f. Here's what I'm going to do. Remember what your del is. It's the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. And I'm going to cross it with that f1, f2, 0. So I've got an I, j, k, I, j. Here's my ddx. Here's my ddy. Here's my ddz, another ddx, another ddy, and my f1, my f2, my f3, my f1, and my f2. So in the I direction, I'm going to have ddy of f3, which is 0, because f3 is a 0, minus ddz of f2. Now, f2 only has x's and y's in it. This is just a two-variable function. So ddz of f2 is going to be 0. So in the I direction, I'm going to get 0. Now let's look at the j direction. In the j, I'm going to have ddz of f1. And again, f1 only has x's and y's in it. So that's going to be a 0. And I'm going to subtract ddx of 0. So I don't have anything in the j direction. So let's look at what we have in the k direction. In the k direction, I have ddx of f2 minus ddy of f1. And that's all in the k direction. And other than having the k, that's my definition of curl up there. So Stokes' theorem really is an extension of Green's theorem. Green's theorem is just a special case of Stokes' theorem. All right, let's take a look at the curl of the vector field, just an example. So here's an actual three-dimensional vector field, and if I want the curl, I'm going to take ddx, ddy, ddz, and cross it with negative 3yz, negative 4xz, and 6xy. So I'm going to have my I, j, k, I, j, ddx, ddy, ddz, ddx, ddy, and minus 3yz, minus 4xz, 6xy, minus 3yz, minus 4xz. So my i's are going to be 6y minus a negative 4x. My j's are going to be, ddz of that is going to be minus 3y and a minus 6x in the j direction. And in the k direction, taking the derivative here, I'm going to have a negative 4z minus a negative 3z in the k direction. Let me double check that. Y, whoops. Yeah, I got a mistake in the first one. Y, that leaves a 6x. And my backwards, the z goes away, minus 4x. And the j's, the z goes away, minus 3y. Here, the x goes away. So, yeah, that one's wrong too. D dx, that leaves a 6y. So I'm going to have 10x in the I direction, minus 9y in the j direction, minus z in the k direction. Okay? All right. Here's what Stokes' theorem says. If you have a line integral, you can turn that into a surface integral of the curl of the function dotted with the dA. And the curl is the gradient, or not gradient, the del crossed with f dotted with dA. And compare that to Green's theorem. It looks exactly the same. The only difference here is that we don't have a dot because our dA is always the k value. It's easy to figure out. Okay? So it's really the same theorem. All right. This also works both ways, and that's really, really important. Okay? Sometimes we're going to have a line integral and turn it into a surface integral, but sometimes this is really useful to take a surface integral and write it as a line integral as well. So this is a good thing to know. Let's look at an example. Okay? So the figure below, we have an open cylindrical can, so no top in it. Okay? It's standing on the xy plane. The curve C is a circle of radius 4 centered on the z-axis. And we're given that we want to find the surface integral of the curl of that function dA. So as soon as I start seeing curls in my work, I start thinking Stokes' theorem. So the line integral is equal to the surface integral of the curl of the function dotted dA, and the curl of the function dA is what we've got, so it'd probably be easier to go this way and find the line integral. And so that's what I'm going to do. Okay? So I'm given the curl of the function. That means that this is my function. F is the function negative y, x, and z. Okay? The dr is the boundary of the shape. Well, that's this curve right here. That's on the shape. Okay? So let's see. It's a circle. It's going counterclockwise, so I'm going to say that that's cosine of negative t times 4, because my radius is 4. Sine of negative t times 4. And the z value is a constant 2. So there's my r. I can clean that up. There's an identity that says that the cosine of negative t is the same as cosine of t. So I'm going to clean it up. But you don't need to. Your work will still work. Okay? For sines, the negative comes out because sine is an odd function. 4 there. And a 2. Okay? But you don't have to. It still work. You have some extra chain rules in your calculations, but it'll still work out. So there's r. I need dr. So dr is going to be negative 4 sine t, negative 4 cosine t, 0 dt. And when I plug my parametric equations into f, my negative y will be a negative 4, it'll be a negative 4 sine t. Come back here. My x will be a 4 cosine t. And my z is just a 2. So now I have my setup. My f, 4 sine t, 4 cosine t, 2, dotted with my dr, which is negative 4 sine t, negative 4 cosine t, 0 dt. And to make this work, this would have to be t goes from 0 to 2 pi to make this work. Let's put the rest of it up here. So from 0 to 2 pi, I'm getting 16 negative 16 sine squared t, and then minus a 16 cosine squared t plus 0 dt, which you can see from 0 to 2 pi is negative 16 dt, so that's going to be negative 32 pi when I integrate it out. Groovy? Okay, let's do one more example. All right, so we're given the curl of a function, and we want to find the line integral. C is a circle of radius 5 centered at the origin. C is in the xz plane oriented counterclockwise when viewed from the positive y-axis. So let's draw this. Here we go. It's a circle kind of back here. There's back behind. And when we're looking at it from the positive y-axis, so there's my eyeball, it's going counterclockwise, so it's going that way. And if I use the right-hand rule, that's my direction. Okay, so again, I've got a curl, so that's telling me probably Stokes' theorem. I don't want to try to uncurl that function. That's going to be too much work, so let's remember Stokes' theorem. It's f dotted with dr equals the curl of f dotted with dA. We want to find f dotted with dr, so this is what we're going to calculate. So I need to take the double integral of curl of f dA. Curl of integral of 0, comma, x squared plus z squared, comma, 2, dotted with dA over that surface, over that circle. Okay, well, we're working in a circle, so we're going to move to polar coordinates. The circle is in the xz plane, so I'm going to put my polar coordinates in x and z. So I'll make x be equal to r cosine theta. Whoops, not y. I'm so used to doing that. Z will be my r sine theta. Y will just be my y. And x squared plus z squared will be my r squared. And oh, look at that. It's x squared plus z squared. Isn't that convenient? So I'm going to have the double integral of 0. X squared plus z squared will be my r squared. It's an r right there. There's a 2. And now I need my dA. So dA is a vector. You take a unit vector that's perpendicular to the surface in the direction of orientation, which is j. So there's my unit vector in the direction of orientation times the area of the circle. Now the area of the circle is 5, but I have an r up here, so I can't use just 5 because I don't have a constant in my integrand. So I'm going to have to use r dr d theta. And as I integrate this, my r is going to go from 0 to 5, and my theta is going to go from 0 to 2 pi. So this is going to work out to be the integral from 0 to 2 pi, 0 to 5 of r cubed. I got an r squared here and another one there. And the x's go away and the z's go away, so that's it. Dr d theta, which is easy to calculate. That's going to be 1/4 times 625 times 2 pi. So my answer is going to be 625 halves times pi, and we're done. So for me, always I set these things up. I actually write out Stokes Theorem first and figure out what it is that I know and what it is I need to find. And that tells me whether I need to do the line integral or if I need to do the surface integral before I do anything else, before I start to plug in, before I start to figure out what coordinate system I'm going to use or anything like that. Got a little bit of vocabulary. Okay, so let's go back to line integrals really quickly. Okay, we want to know if a vector field is the gradient of a function. And there's a test for that. Remember, we look to see if the curl is equal to 0. This works in 3 dimensions as well as 2 dimensions. So if the curl is equal to 0 for every point in the domain, then we know that this is the gradient of a function. In 2 dimensions, it's the gradient of just a scalar function. In 3 dimensions, though, it's the gradient of a vector field, and so we call that the vector potential instead of just the potential. Also remember, if the curl of f is 0 for all points in the domain, that means that you can use Fatoli in 2 dimensions as well. Okay? And some vocabulary for this, in case you see it on the test, is the word irrotational. Has no curl, so it has no rotation. That's how you remember it. If it's not irrotational, then it's rotational. That means that it does have some curl somewhere. At least one point in the domain has got a curl that's not equal to 0. All right, there's some more things that go along with divergence, so let's look at that. If you want to know if the vector field happens to be the curl, so before we're looking to see if the vector field is the gradient of a function or the divergence of a function. Now we want to see, is the vector field the curl of something? Then we use what's called the divergence test. We check the divergence. If the divergence is equal to 0 for all points in the domain, and the domain is nice, that means it doesn't have any holes in it, okay, then f is the curl of some other vector field. And we've got some notation for that. F is called a solenoidal function. Sometimes it's called an incompressible function. Now, this gets into some physics that I never studied, so I can't tell you a whole lot about this, but when you have a vector field, there's a way to break it into 2 parts. Remember when we had vectors and we looked at projections, and we looked at the part of the vector that was parallel and the part that was perpendicular? My understanding is that if you take the vector field, that you can break it into 2 parts, and part of this is going to be the divergence of some other function, and the other part is going to be the curl of some other function. So it's kind of like breaking it into components somehow. But that's I can't tell you more than that. That's physics that I never really studied. All right, but those of you who are getting farther along in your physics, you may know more about this and you can tell me about it. And that, ladies and gentlemen, is the end of the semester. We'll work problems in class this week. We'll have time to look at example questions from the practice exam as well. And I'll see you then. Take care. Bye-bye.